Hi, welcome to the Calculus 3 assignment practice series. And we are in this unit, partial derivative unit. And this is our assignment number 6 worksheets. And we are working on the directional derivatives. There are some very interesting problems in these sections here. So, okay, let's go to our worksheets and start to practice some of the things we learned in the, the section number 6 about the directional derivatives here. Okay, let's go to our worksheets here. I'm going to work several problems here to show you and how to do some of those problems. So the first problems here I'm going to show you is how to find the directional derivatives here. So remember, right? So we said the direction derivative, what is the formulas here? So the formulas here, we say that this is the AB. So what is here is the partial of x, and so partial A, B, x, and then the u's here, we say it's times A. Well, I guess this is not a good, so it's times A. So I should say here, let's put a different ways here, x0, y0. So maybe that is better notations here. Okay, so here, let's see here. Okay, so, right, so this is x0, y0. This will be equal to the partial of the x0, y0 and times A plus the partial x0, y0 times B. What is AB's here? U is a vector, right? So this is, we say it's the AB. But the U has to be what type of the vector? Unit vectors, right? This is what we learned at. That means the square roots of the A square plus B square has to be equal to 1. Okay, so now in here we said we find the directional derivatives at this point, x0, y2, and the theta is equal to the pi over 3. Instead of giving us the vector, they say, hey, this vector have a theta equal to the pi over 3. Since I know this is, so this is the unit vectors, right? So basically, what is my thetas here? So the A is going to be equal to what? Will be equal to the cosine pi over 3, right? And the B is going to be what? The sine pi over 3, right? Because if in the xy things here, so we say I have this is my u vectors here. If this is pi over 3, right? So what is the A's here? A is the cosines, right? Okay, so as that's basically this problem try to test you here. So see, understand, instead of giving you the AB, I give you the angle. So it's the same thing. Okay, so let's take a look at partial fx here is y cubed minus x, right? And then you substitute to this specific point, 1, 2, will give you what? Give you 6. Then we said f of y here, this is 3xy squares, right? Then you plug in this y, the 1, 2. So what is here? Is 12, right? Okay, so now we can use our formula for the directional derivative. So this is du y2 is equal to what? Is equal to the f of x times A. So A is cosine. So it's 6 times cosine what? Pi over 3. Okay, plus 12 times what? Sine pi over 3. And so I know the cosine pi over 3. What is the cosine pi over 3? It's a half, right? So this is the 3 and the plus, and what is the sine pi over 3? So this is the square root of the 3 over 2. Okay, so my final answer is 3 plus 6 square root of the 3, right? So this is the directional derivative. So be careful in here. Basically, they just want to make sure if I give you an angle, how do you find the vectors, right? Okay, so then the remaining problems for this page is very mechanical. So the next one I'm going to work is the number 14 here. So that I want to find the directional vector according to these vectors here. So the first, let's say, the del, the del g's, so that's the gradient vectors, right? So it's gu, okay, gu, this is 2u e to the negative v's, right? And then gv, so it's a negative u square e to the negative v, correct? Okay, now you plug in this g for the what, 3, 0. So what is your gradient vectors going to be? It's going to be, so 0, this is 1, so it's a 6. Oh, here. Then the 3 is 9, so it's negative 9, right? So this is my gradient vector. And then now I know the du. So now I'm doing it for the du g30 will just be your gradient vector dot product of the v's here. So the purpose of this ones here is because I know the directional vector have to be what is unit vectors, right? So if you take a look at the v, what is the length of the v here is 3 square plus 4 square, so it's a 5. So it's not a unit vector. So I need to do what? I need to change it to the unit vector. So I divide by 5. So this will be 3 over 5 and 4 over 5. So now I can find my directional derivative of the g30 will just be the 6 to the negative 9. And then you dot product of what? 3/5 and 4/5 here. All right, and then you just use your calculator and you can get this is 18 over 5, so it's negative 18 over 5 here. Okay, so now the next questions I like to do is number 18. I think this is a pretty good questions here. So they want to see the du f22. Okay, so let's try to write down here. So du, the f22. Okay, based on our definition will be the gradient vector f of what? Gradient vector of f22 dot product my what? U vectors here. Okay. Okay, so what is the gradient vector? So I have a gradient vectors here. I have a use here. So what is this dot product? If you still remember, so this is to try to test you or to see you understand or not. So try to remember that this is we call this scalar projections, right? So the scalar projection of the B onto A. Do you still remember here? What do we write here? We say this is the scalar projection. So this is B to the A, right? B to the A's here. So it will be A dot B over A's here. So what is this one means here? So this one, okay, based on my scalar projection. So this is what? So this is the scalar projection of del f to u, right? So because you said where is this a? So a is the u's, right? So it's 1 because we say it has to be 1, right? It's a unit vector. Okay, so now let's see what's that mean. How do I find the values here? So this one is a 2, 2. So this one, so this is 2. And this is 2, right? So this distance is 2. Okay, so we know this is scalar projection of the gradient vector to u. So you kind of extended the u. So that means I need to project it, right? So in here, the projections here, right? Okay, so this is how do we define, right? So it's kind of like we say, you have a light here, you're shining the light through here, right? So this one's here, so this green lines here, right? So this green line is what is my del f22 dot u, right? And then you just kind of the measuring. So if this distance is 2, so this distance, well, probably is around 3, right? Okay, so because probably around 3, but it's going to the opposite direction of the u. So I know that this derivative, partial derivative, is approximately to the -3. All right, so that means the rate of the change is going to the, it's kind of the obvious, it's go to the opposite direction to the u's, right? So that's why you have the -3. And I think this is pretty good problems and get to a good understanding what is the, the kind of the directional derivative, and then kind of review whether you still remember in our previous unit about the scalar projections here. Very interested, okay? All right, so now the next one here, I'm going to take a look, is the problem number 28 here. So this one also show you something different here. I said here, find the direction in the directional derivatives, okay? And at the point, and it has the value 2. So that means I'm going to find that vectors here. Okay, so let's take a look at del f of x, y, right? So that means is partial x is what? Is 2x plus y cubed. And the partial y is just 3xy squared, right? This is my gradient vector. Then plug in the point 2, 1. All right, so 2, 1, 2 plus 1 is 2 times 2 is 4, so it's 5. 2, 1, so 2 times 3, so it's 6. Okay, so here is 5, 6. All right, so now I need to find this. So basically, I need to find the unit vector u's, right? Okay, so that's basically, so that means, and I'm going to find, that means because then, so the del f, right? So the del f dot product u is here, right? So I have, this is the 5, 6 dot product, let's use here, let's say it's AB here, right? So it's dot product AB. And I said the directional vector, right? So the directional derivative has to have a value is equal to 2. And so I know here, that means if you find the here, that means what is 5a plus 6b has equal to 2, correct? So now I have an equation is 5a plus 6b equal to 2. So I want to find this unit vector. So I need to solve system of equations. So I need to have one more equation. But I know this is what? This is a unit vector. So what that means here? That means a squared plus b squared is equal to 1 here. Okay, so now you can say that a squared is equal to, and so the a squared is equal to the 1 minus b squared, and or you can say, yeah, maybe this one is easy. So you say a is equal to 2 minus 6b over 5 here. Okay, so the 2 minus 6b over 5 here, and then you'll be able to solve it. Okay, so now let's try to solve this, the system of equations here. Okay, so a is equal to here, and then Or you can say the, okay, so let's do the B. Okay, so let's solve for the A's here. So it's about the same things here first. Okay, so I said the B is equal to the 2 minus 5A over 6. Okay, and now let's just try. Okay, so now here, this is A squared plus B equal to 1, right? So I would say that A squared plus B is 6, 2 minus 5A square equal to 1. So I have A squared plus 36, 2 minus 5A square equal to 1. And then I just FOILed it and combined it. I got a 61A square minus 20A and minus 32 equal to 0. Then use the quadratic formula. So I say A equal to 61 minus B plus minus 6 over, okay, 57 here. Okay, that's what I use quadratic formula. Okay, so when the A is equal to, you know, the 61, the 10 plus 657 square roots. So the A is approximately to the 0.9065, or the A could be equal to 61, 10 minus 657, and the A is approximately to negative 0.5787. Okay, so when A is equal to this number, then the B going to be equal to negative 0.4221. Then here the B going to be equal to 0.8156 here. So that means that I can find the two directional vector, you know, the unit vector. So one is 0.9065 and the negative 0.4221, or you can have this one negative 0.5787, 0.8156. It's just a very tedious, you know, it's just a very tedious algebra. I just like to show you another different type of the problems here. Okay, so now let's take a look at the next problem here. Okay, so next unique problem is number 49 here. So the number 49, so we have a function z equal to the xy. Find the gradient vector. Okay, let's see z. So gradient vector will be the partial x, so it's y, and the partial y is x. So the gradient vector 3, 2 will be equal to what? Will be equal to 2, 3, right? Okay, so then use the gradient vector to find the tangent line to the level curve f of xy equal to 6 here, right? So that means 6 is equal to xy here, right? So this is my level curve here. So my level curve, and probably will be something like here, right? Like this. So remember, right? So when we did the gradient vector, so we know the gradient vector. What is the gradient vector again? It's the one, right? So it's the one they're going to be what? Perpendicular, right? So this is we call it a gradient vector going to be perpendicular to your level surface. All right, so now I want to find the tangent lines, right? So the tangent lines here, that means this is the tangent lines here. So the gradient vector will be the perpendicular vectors to the tangent lines here. So that's what I can find. So if this is the 2, 3, right? So if this is 2, 3, so what is the slope of this one? the slope is what? Is 3 what? It's the 3/2, right? And then, okay, so the 3/2, so the tangent, so this is the 3/2. So the slope here for the tangent lines here. So the slope for the tangent line, so what will that be? Slope will be the tangent line will be the -2 over what? 2/3. And then you are going to the point, this point is 3, 2, right? So that will be, so what's that mean? So that means y minus 2, right? So 1 minus 2 will be equal to the -2/3 x minus 3 here. So if you simplify it a bit, then we know this will be the 3, the y minus 2 plus 2, the x minus 3 equal to 0, right? Or, so this is kind of like the geometry approach. Or you can just say here, the del F here, right? So the del F 3, 2, you can just dot product, right? So the x minus what? X minus 3, y minus 2, right? Because they're going to passing through this point. And then you will get the answer quite faster. This will be 2 to x minus 3 plus so this is a 3, yeah. So then the delta 3, 2, this is will be equal to the 2, 3, and delta, this is dot product x3, y minus 2 here, right? So it's 2x3 plus, right, 3, the y minus 2 equal to 0, right? So because we know that then your dot product it will be equal to 0, and so that's what is our, that's what is our lines, right? So the lines here is you're going to get a 2x plus 3y equal to 12 here. All right. So that you can use it, in the R2, you can use the geometry approach like we find here, or, directly you can just, instead of use the geometry approach, you can just use what we just did here is your gradient vector, your dot product vector, right? It will be equal to 0, right? Because it's a perpendicular here. All right. So that will be a lot easier to do. Okay. So now, let's take a look. Okay, so the next one here I like to take a look is number 54 here. So this is the one. Okay, so let's take a look here. They say at what point on the ellipsoid x squared plus y squared plus 2z squared equal to 1 is the tangent plane parallel to the plane x plus 2y plus z equal to 1. Okay, so remember that we said this is the function of x, y, z equal to 1. So what do we call this? We call this is the level surface, right? So the level surface for the ellipsoid here, right? So now this is because this is level surface, then the gradient vector, so the gradient vector del F will be what? Will be the normal vector to this surface here, right? So we say, okay, del F here, okay, so let's see here. So I have 3 gradients, right? So it's Fx, Fy, and Fz. So this will be the 2x partial y, 2y, and what is the 4z here. So this is the what we know, that's what is the gradient vectors. So this is the what? This is the normal vector to the surfaces, right? Like we talk about, it's kind of like the line sticking out, the surface is perpendicular. Okay, so now that find the point that the x0, y0, z0 is a point on the ellipsoid. Okay, so that's the ellipsoid, right? Okay, because this one is in here, right? Because they say the tangent plane has to be parallel to x plus 2y plus z. So x plus 2y plus z is here. Take a look at this one. If this is the planes, right? So what is the normal vector for this planes here? This is the 1, 2, 1s, right? That's what we talk about here. And because this is the what? This is the normal vectors for the planes, right? So this ones here has to be parallel to my gradient because the gradient vector is also the normals, right? So now I find this point. So I know the 2x0, 2y0, 4z0 has to be some type of the constants times this one, right? Because it has to be parallel, all right? So now I know the x0 has to be what? K over 2. Then y0 has to be k over 2. Then the z0 has to be k over 2, 4 over k over 4s, right? Okay, now I substitute all this value back to my ellipsoid, right? So I will say this is k over 2 to the square plus k over 2 to the square plus 2 the k over 4 to the square, right? And what is going to be equal to what? Equal to 1. Then I'm solving for k's here, right? So this one is pretty easy. So the k, so I have a 1k, just 1k, 2k square, and the 3k square. So basically, so here I find it's, so here you can say here, this is the, okay, so the k square and y0, I'm sorry here, the y0, this one's here, you need to be careful. Y0, 2y0 equal to 2. So y0 is only equal to what? Only equal to k, right? So I need to be careful here. All right, so here this is a k square, right? So this is, I need to be careful. This is a k square. And then I'm solving for k. So I finally, I trust you guys can be doing the algebra solving. So the k is going to be plus or minus 2 and the square root of the 2 over 11 here. Okay, so we have okay, so we have the tangent planes, right? So or the what points, right? So I know the points here. Okay, because the k can be plus minus 2 the square root of 2 over 11, right? So the points here could be, so what? So k equal to 2, if you put the plus over 2, so x0 will be not a vector, so here is a point, right? So here's a point here. So when the k equal to the positive, so k over 2, so it's 2 over 11. And the k here, this is a 2 over 211. Then k equal to over 4. So that means 1/2 2 over 11, right? I just substitute here. So this is my first point when the k is equal to the 2 over 11. Then another point is here is when the k equal to the negative 2 over 11. So what is my point here? My point will be the negative 2 over 11 and the negative 2 over 11 and the negative 1/2 2 over 11 here. All right. Okay. So okay, let's take a look at problem 55. If you are still not quite clear, right? So this one's here, it will tell you, see here, they said, are there any points on the hyperboid x squared minus y squared minus z squared equal to 1 where the tangent plane is parallel to the plane like this? Okay, so still, this is my what? This is my level surface. Right? And then for these planes here, right? So this one here is x plus y minus z equal to 0. So what is the normal vectors here? That's why we say the normal vector for this plane is what? Is 1, 1, negative 1, correct? All right. And then also by the gradient vector. So if this is my f here, right? So then the gradient vector of the f is a partial f of x. So it's what? Is 2x minus 2y minus 2z here. Okay, so let's see, and the given point, x0, y0, z0 on the hyperbolic. All right, so because the tangent plane parallel to this plane, that means my gradient vector going to parallel to these normal vectors, right? So that means for this point, 2x0 and next to y0, next to z0 is going to be equal to what? It's a constant times the normal plane here. Normal vectors here is 1 and negative 1. Now, let's solving for case, right? So now we're solving for case here. So okay, so we have like so we do the same ways, right? So x0 is equal to k over 2, and the y0 is equal to negative 2 over k, and then z0 is equal to the negative 2 and the negative k, so it's a positive case here, right? Then you plug in, right? So then you plug in to your hyperbolic, so you have like a k over 2 to the square minus negative k over 2 to the square, and minus 2 to the k to the square equal to 1. Okay, then you will find here, okay, so the right, so now this one cancel, so you will find a negative k over 2, right? So you find the negative k over 2 square equal to 1. Is that reasonable? No, right? So we said no such k. I cannot find such case here. So now we know no such point. x0, y0, z0 exist on the hyperbolic, and such that the tangent plane parallel to the plane x plus y minus z equal to 0 here. All right, okay. All right, so that's number 55. Let me do one last one here, because those type of problems really give it a good ideas here. So we said, where does the normal line to the paraboloid at the point 1, 1, 2 intersect the paraboloid at the second time here? Okay, so every time we see this, so I know this one's here, this is can change to x squared plus y squared minus z equal to 0. What do we call this again? You know, we call it is level what? We call this is a level surface, right? So we call this is a level surface. So what is level surface? That means this is my capital F of x. All right, so the capital of f of x, and then find the gradient. So the gradient will be partial for x is 2x, partial for y is 2y, partial for z is negative 1 here. Okay, now at the point, so substitute the point for my gradients 1, 1, 2. So what is here going to be 2, 2, negative 1. All right, okay, so this is the normal lines, right? So the at 1, 1, 2, right? So in here, so I know the normal line at the 1, 1, 2, right? Because then the gradient vector is their directions, right? So 2, 2, 1 is their direction. So I can write down the lines, x passing through. So it's 1 plus 2t, and the y is equal to 1 plus 2t, and the z is equal to negative, so it's 2, right? Yeah, so it's 2, so it's passing the point. So here, this is 2 minus t here, right? So remember, that's the line's definition, right? So those are the point. So that's the point, and the line need to have a directions, right? So this is the direction, right? So this is a 2, 2, negative 1. So that's what is my lines here. So let's say the, hey, does this line, you know, the intersect the parabola, the second lines here? Well, that's a substitute, right? So let's say, okay, let's take a look here. So then the z, we say is 2 minus t is equal to, let's substitute back to my parabola. So it's 1 plus 2t the square plus 1 plus 2t the squares here, all right? So then this one is 1 plus 4t plus 4t square plus 1 plus 4t plus 4t square. Then you can solve that. So here I have 8t square plus 9t plus 2. 90 plus 2. Okay, so no, the plus cancel, right? So here, this one will be what? Equal to 0. So then the t, I can have 8t plus 9 equal to 0, right? So t equal to 0 or t equal to the negative 9 over 8. When t equal to 0, that's the point of 1, 1, 2, right? So now you plug in the t equal to the negative 9, then you plug negative 9 over 8. So you get the point here, you plug in here, will give you negative 5, 4, 5 over 4, negative 5 over 4, and the 25 over 8. So this is another point. So that's true. This normal line going to intersect this paraboid at twice, right? So the first point at 1, 1, 2, then they're going to passing through that, and then the second point is negative 5, and 25 over 8. Okay, that's it. So this, like I said, this assignment have many very interested problems. And the whole things here, you know, we use the concept of gradient vector is perpendicular to the level curve or will be the normal line to the level surfaces here. Okay, so use that concept, now I think you'll be good. All right, I hope that this help you to understand this homework for this problem assignments here. Okay, so that's it, and you have a good day. Okay, bye.